for how much amount of copper is saved in auto transformer. Okay, and the difference between auto transformer and two winding transformer, those parts we derived in the second module. Okay, and we saw the applications and advantages. In three-phase transformer, we studied the construction, working principle, and the various type of connection of three-phase transformer. So this is where we stopped in the last class. I'll just again go through this. If you have any doubt, please look at the screen. So this connection is called as star-to-star connection of three-phase auto transformer. Here, the primary is star connection as well as the secondary. Both of them have been connected in star manner. The high voltage winding is denoted with capital letters and low voltage winding is denoted with small letters. This is a general gesture followed by manufacturers of transformers. So if you see a practical transformer, one side of the transformer will be mentioned in uppercase letters and the other side will be mentioned in terms of smaller case. Okay, so that indicates uppercase means that part is high voltage part and the lower case means that part is low voltage winding part. Okay, so that is again denoted as HV and LV sides. HV stands for high voltage side, LV stands for low voltage side. Okay, and this side, the primary side, it is connected in star connection. We know that what a star connection is. At least one terminal of each phase winding are connected at a common part. Look at this diagram. These two are equal. So if you draw like this, you will understand better. That is why I'm drawing like this. So this phase has two terminals, namely, let us call it as A1 and this as A2. And if it is B phase, this would be B1 and this part will be B2. Similarly, C2 and C1. So all the second terminal of all the three phases have been connected at a common point, which is called as neutral. And the first part is given for external connection. For example, if this is the primary side, these three will be connected across source. So what is the source for a transformer? It must be a AC source, okay? And these three will be connected across the load. Okay. Since primary and secondary, both of them are in star connection, the diagram will also look the same. Okay, so in high voltage side, we have mentioned them with uppercase letters. In secondary side, you should be mentioning that with lowercase letters. Okay, that is the only difference you have to draw, and you have to explain everything while writing in the examination. Okay, so when you explain the star to star connection, you start from this. The primary winding of this transformer is being connected in star manner. In star connection, at least one terminal from all the three phase windings will be connected at a common junction. All the three phase windings will be connected at a common junction. Okay, it will be having a neutral point. This is suitable for 4-wire 3-phase systems. Okay, so these points if you have written, then it will be given full marks. And know the working difference between these two. For a star connected transformer, this is the voltage equation. Phase voltage is 1 by root 3 times of line voltage. That part I explained in the last class itself. If you forget, I will explain again. So all the three lines have been connected with phase windings. if I connect a voltmeter between two lines, that is R phase and Y phase, then it will be called as line voltage. Okay. If I connect a voltmeter across a particular phase, then it is called as per phase voltage. Okay. When comparing to these two, this value will be higher. Okay. Line voltage will always be higher in star connection since it has two winding parts. Okay. We combine R phase as well as Y phase. Both of them have been combined. So the total voltage across this voltmeter will be very high compared to this, because this part is connected between R phase and neutral. So what this voltmeter is going to show you is the only EMF induced in R phase alone. Okay, but this meter will show you the EMF induced in R phase as well as Y phase. Okay, that is why always line voltage is greater in star connection. Okay, so if I need line voltage, VL1 is equal to square root of 3 times of 3 phase. Okay, and this one, look at this. So this is called the voltage transformation ratio. Otherwise, I would have told you this as 1 by K. What is K? K is called as transformation ratio. Otherwise, we can call K as V2 divided by V1. So this is an indication at which rate the voltage is transferred from primary to secondary. So for example, I told you this part is the high voltage side and this part is the low voltage side. So high voltage side must be having, for example, let us take 6,600 volts versus 440 volts transformer. So obviously 6,600 volts side will be bigger compared to 400 and 440. So 440 volts. Okay. So what is the difference in these two? What would be the difference? First of all, when you see a transformer, how will you identify it as a step-up transformer or step-down transformer? Just by seeing, can we identify whether it is a step-out or step-down transformer? For example, I'm removing the outer part of the transformer, the case. Okay, you are allowed to see the coil of the transformer. So just by seeing the winding of the transformer, can you tell which part is high voltage side and which part is low voltage side? Can you? Is it possible? Just by looking at the winding, and we can identify the high voltage and low voltage sides. Is it possible? It is possible. We have to check the thickness of the conductor used in both the windings. So when the thickness is very high, that part will be carrying more current. Okay. When current is high, current capacity is high, that part must be low voltage winding. Okay. So keep that in mind when you go for a practical transformer. You can easily identify the high voltage and low voltage sides, but before that you have to remove the outer case of the transformer. So in our laboratory we can see that. I'll remove the outer case and show you how to distinguish the high voltage and low voltage sides. Okay. So this explains in which ratio the voltage is transferred from primary to secondary side. For example, take this as an example. So for this example, 6,600 bar 440 volts transformer, what will be the K value? K must be, yes, okay. Please don't turn on your mic and it may be interrupting the class. So for this transformer, the transformation ratio must be K equal to 440 divided by 6,600. So looking at this diagram, we can identify the value of K. So it must be, for example, it must be 0.05. Or for example, it may be 0.2. Any value. I don't have a calculator, so I'll just give an example. So K value here is 0.2. So what would be A value? A must be 1 by 0.2, which is 5. So the voltage is stepped up or stepped down 5 times from primary to second. So this is how we are calculating the transformation of voltage from one side to another side. Okay. Similarly, we saw the star to delta connection. In delta connection, line and phase voltage will be similar. Okay, this is what I explained in the last class itself. So VL2 is equal to VPS2. The suffix 2 denotes it is in the secondary side. Okay. So what are the advantages and disadvantages of that one? Star to delta connection. And next we saw what is delta connected transformers. Delta to star connection, that is primary side will be delta connected and secondary side will be star connected. And finally, delta to delta connection. So both the primary and secondary will be delta connected. Here we don't have any doubt. Whatever you give us the input, the same output will be induced in the coil. Okay. Based on the transformation ratio, that is very important, A value. Okay. And open delta. Next one is a parallel operation of a single phase transformer. This is where we stopped in the last class. I explained you the operation of transformers which are acting in parallel. Okay. So the main aim of parallelly connecting two transformers is to support the load. For example, the load may be having higher rating than the supply system. So we will be using 2 or more transformers connected in parallel. Then we will support the entire system. Okay, using that. Okay, instead of going for a single transformer supplying the entire load, when you go for 2 transformers, we have a plenty of advantages like reliability, continuous operation, maintenance will be easy. Okay, so these are some advantages of parallel operation of transformer. Okay, so those are the points I explained in this slide. And there are some conditions to be connecting 2 transformers in parallel. So we cannot directly couple 2 transformers in parallel. So first we have to check the voltage ratios, polarity, percentage impedance, and phase sequence. So those are very important. And I explained what are the impact of these conditions. What will happen if they are not connected as per this condition in the first module itself. Okay. So if you have any doubt, please go through that video. Here now we are going to derive an equation for load shared by 2 transformers. So what are how much load? It is not necessary they should be equally sharing the load. For example, I'll explain with generators. I have 2 generators named as G1 and another one is G2. Look at these 2. Just by looking at this diagram, you can identify that G1 is smaller compared to G2. For example, I'll tell this as it is a 1 kVA generator and this is 3 kVA generator. And these 2 are coupled in parallel and they are sharing a load of it's a variable load. They are sharing a load of 3.5 kilowatt. So while I write this example, you should be getting a lot of doubts why the generators are mentioned in kVA and the load is mentioned in kilowatt. If you have such doubt, please go through your first semester subject called electric circuit. In that they would have clearly explained what is what is the difference between kVA rating, kilowatt rating, and kVAR rating? Reactive power, real power, and apparent power. What are the differences between all these powers? They would have explained you. Please go through it. I'm not going to explain you that now. If I start to explain that, it will take more time. So see that. You should be getting that doubt. I just remind you. Generators are mentioned in terms of kVA and load is mentioned in terms of kilowatt. Okay. So look at this. This generator is a 3 kVA, so it is not sufficient to meet this load. Okay, as well as this generator is 1 kVA, so this is also not sufficient to meet this load. So to meet this load, to supply the demand of this load, these two generators are coupled in parallel. The circuit, it is not a circuit diagram. I'm just giving an example. Don't get confused with this. Okay. So these two are coupled in parallel. So totally we will be getting 4 kVA. So now the total power is meetable by these two generators. Okay. So for example, if the load is reduced, for example, during morning time, I'm not using many loads. Okay. So now the load is reduced to 1 kilowatt. This generator alone is sufficient to meet the load. But what we will do is, the sharing ratio will be reduced. For example, initially, these two generators were functioning fully. The full power capacity is given to the load. 1 plus 3, 4 kVA is applied to the load so that we can meet 3.5 kVA of kilowatt of load. Okay, now the load is reduced. The same ratio will be maintained. Here it was 3. Here it was 1. Now the ratio will be 3:1 or 1:3. Okay. When the load is reduced, this ratio will be also be reduced. Sorry, the ratio will be kept constant. What will happen is, first transformer will give you 0.11 or 0.33, and second will be sharing 0.99. Do you understand what I'm telling? The ratios of how much load is shared will be kept constant. That will not be differing. Okay. So even if the load is reduced, and look at this example, 1 kilowatt, we can easily send the power with help of this 3 kVA generator. Okay. Since the generator generates 3 times of the load demand. Okay, the load is requiring only 1 kilowatt. The generator is generating 3 kilowatts. But still we will share the load and send that to the load. Okay, this is the beauty of parallel operation of transformer. What will happen now is, we can save a lot of energy during this. For example, when 3 kVA total power is given, current will be very high, obviously, when the load is measured in terms of current. Okay, when full load is given, current value will be high. So what will be happening to I square or loss? During full load condition, what will happen to I square or loss? Can anyone answer? At full load condition. What do you mean by full load condition? The entire capacity of the machine is met at that condition. Is called as full load condition. For example, a generator is mentioned 20 amperes to 20 volts. That means you can load the machine up to 20 amperes. Okay, that is called as full load. If you load the machine for 10 amperes, then it is halfly loaded, half load of the machine. Okay. So what will happen at full load condition? I square R will be very high, isn't it? So instead of increasing this loss, copper loss, I'll share this current requirement with another generator. So what will happen to my loss? Now the loss will also be reduced. Okay, so it has plenty of advantages when you connect two generators in parallel. Okay, so see this diagram. Two transformers have been connected in parallel. So this side has been connected with the source denoted as V1. This side we have connected the load. So what is the primary side? This part is primary side and this part is secondary side. So look at this diagram. Transformer A and B, The primaries of transformer A and B is connected across source. The secondaries of transformer A and B are connected across the load. Okay. Initially, the switch is kept open, so no load will be passing through this. So no current will be passing through this, and the generator voltage will be induced. Okay. Now the switch is closed. Load is gradually increased. So when load is gradually increased, the current will be increasing. Since the transformer is receiving current from both the transformers, the load is receiving current from both the transformers, the total current passing through the load is IA plus IB. IA is current from the primary transformer, A transformer. IB is the current from B transformer. Okay. Next. So this is the equivalent circuit of the transformer. So two branches indicate this is the impedance of A transformer, this is the impedance of transformer B, and they have been connected in parallel to the load. Okay. So what will be the sum of these two? The current passing through first branch is IA, the current passing through the second branch is IB. Here also it is I. Okay. So that is splitted here into two. Again, they are joining at this junction and passing through the load. Okay. So first, the load shared by transformer A, which is given as V2 into IA. Look at this. V2 into IA, go to the previous diagram. V2 is the voltage across the load. IA is current passing through the A transformer. Okay. So that is why it has been written as V2 into IA. Okay. Look at this diagram. So we have two branches. We know the value of this current, I, and we know the values of these resistors, RA and RB. Look at this diagram. So we have two resistors connected in parallel. One current is entering into the junction which these two resistors are connected. Okay, so the junction, this is the junction where resistor A and B are connected. So let us name it as N, point N. Okay. So at the end, the current is split into two. So one is passing through this resistor, which we may give a name IA, and in second branch, the current passing through is denoted as IB. Okay. So what will be if you apply Kirchhoff's current law, what will be the equation here? Can anyone answer? I want to apply Kirchhoff's current law at junction N. So what will be the equation? Please answer. So it's a simple question, you can answer that. I equal to I1 plus I2. So which I mentioned here as IA and IB. Okay, so we can write that as IA plus IB. Okay. So if I need the value of IB, I can use the parallel theorem of circuit theory. You would have studied that. If you want to find out current of one particular branch, you should know the resistance of every branches. Okay. So what is that equation? To know the value of current in a particular branch, I A is equal to total current. The total current is denoted as I into total current into opposite resistance. So we have two branches. The opposite resistance branch, opposite branch resistance is denoted as RB divided by sum of the resistances in the all branches, RA plus RB. Do you remember this? You must have studied this in first semester. Okay. So this is the equation for finding out current in branches. If you want to find out current in this branch, IA, then this is the equation. Similarly, if you want to find out IB, what will be the equation? I into RA divided by RA plus RB. Okay, that theory is applied here. Okay, so I'll explain that with an example. Assume you have a total current of 6 amperes, and that current is entering to 2 branches of different resistors. So this branch is having 4 ohm resistor, and this branch is having 2 ohm resistor. Where the current will be maximum? In which part the current will be maximum? Where the resistance is less, there the current will be maximum. For example, let us name this as I2. Let us name it as I1. Okay. So, as per the theory I explained earlier, I want to find out current I1. So, how can I find out? Total current 6 amperes into opposite branch resistance divided by total resistance. Opposite branch for 4 ohm resistor is 2 ohms. Total resistance is 4 plus 2, which is 6 again. So sum of these two will cancel this. Here the current passing through will be 2 amperes. So the first branch, I'll get 2 amperes of current. So we can either apply Kirchhoff's current law to find out I2, or the same theory, I2. I want to find out I2. I2 can be calculated from total current 6 ampere into what is the opposite resistor for 2 ohm resistor? 4 divided by total resistance is 6. 4 plus 2, that is 6. So 6 and 6 are getting cancelled with each other. So I2 value will be 4 ampere. I2 is 4 ampere. So do you understand this theory? So that same theory is applied here in this part. Okay. So IA is given as total current into ZB divided by ZA plus ZB. Okay. Similarly, load shared by the second transformer, that is transformer B, is given as V2 into IB. Okay. So in the same way, IB has been written as I into I, this total current, ZA divided by ZA plus ZB. Okay. Next one, where I is the total current given as IA plus IB. Okay. So what is the total power shared by these two loads? So total load shared by these two transformers are denoted as PA and PB. Okay. I'll remove all these things. So which is given as PA plus PB, which is V2 into I. Okay. Why I have written that as V2 into I? Yes. The voltage across the load is V2. Current passing through the load is I. So for measuring out power wasted in load, we can directly go for VI theory. VI formula, P equal to VI formula. That is what I have been written here. Okay, V2 into I. Okay, and as well, the load shared by individual transformer is given as PA equal to P into ZB into P is the total power. So that is what have been written here. Okay. And the resistance have been given us. ZA is the total impedance of first transformer. ZV is total impedance of second transformer. As I told you in the earlier session, the current depends on the total impedance of the transformer. For example, if you have more resistance here, then the current value will be lesser. Okay, or more resistance here, the current will be lesser here. So current always selects a minimum resistance path. Where the resistance is minimum, there the current will be very high. Okay, that can be explained with this ZA equal to RA plus Z, J into XA. ZB is RB plus JX. Okay, so this one is very important theory for connecting two transformers in parallel. Okay, read out it. Two transformers share the load only when their equivalent impedance are inversely proportional to their respective load rating. Always the load rating is denoted in terms of current. Okay, so how will you find a machine is not loaded is you need to measure the current value. For example, if you cannot find out whether the transformer is open circuited or not. Okay, so simply by looking at the circuit, we cannot identify. Similarly, if a generator is running, you cannot identify whether the generator terminals are short circuited or open circuited. What you have to do is, you need to connect an ammeter in series and find out the current value. So if you find, so that is what we are doing in using testers. So we will plug the tester inside the plug hole. So if the tester is glowing, then we will identify there is current is passing. Okay, so in the same way for machines we have to use ammeters. So if ammeter shows reading, then it is called connected. Okay, if it does not show the reading, then no load is connected. Okay, so the load value depends. The load value can be identified based on the current rate. Okay, so this theory states the impedance of transformer should be inversely proportional. The equivalent ratio impedance of transformer should be inversely proportional to their current ratings. Okay, so that is what is written here. IA by IB is given as ZB divided by ZA. Okay, out of which I have taken only IA divided by total current equal to ZB divided by total impedance. Okay, so the same has been written here, IA by IB equal to ZB by ZA. Okay, and from the circuit, E2 is the EMF induced in the secondary, which is given as V2 plus. Since these two are in parallel combination, E2 will be the sum of output voltage plus impedance, plus voltage drop across A transformer as well as B transformer. Both of them will be equal. Okay, so this much current is shared by two transformers connected in parallel. Okay, so do you have any doubt in parallel operation? So you just explain the theory, explain the needs, and write what are the conditions for connecting transformers in parallel and how much load is shared by two transformers individually. Okay, so all these details you need to write in the examination. And next we will derive some equations, some problems in the previous sessions. So since we have only one topic rest, we'll see that topic in next class. Can you see this problem? Is it visible clearly? I hope it is visible. Read out this. A 30 kVA single phase transformer has 500 turns in the primary and 30 turns in the secondary. The primary is connected to 3300 volts, 50 hertz supply. Okay, so just by reading out, you can find out some answers. I'll just write the given data here and I'll go to the board and explain you. The power rating has been given as 30 kVA. Number of turns in the primary is given as 500, whereas For secondary, it is 30. Primary side, we have connected 3300 volts source, which is of 50 hertz. Okay, the data has to be determined or secondary voltage on open circuit, which is V2. V1 has been given, and we need to find out V2. Current flowing through the two windings on full load condition. Two windings on full load condition in the sense the transformer is assumed to be operating at full load condition. We need to measure the current at primary side as well as secondary side. And third one, we have to find out the maximum value of flux. Okay, so I'll write all those things. We will derive this. Okay, take the if you have paper and pen, please make a note of it. Can you see the board now? Is the board visible to you? Okay. Can anyone turn on the mic and tell me the given data for the problem? So you need to find out the problem, right? So I'll share that in. Yeah, I'll read it myself. So the transformer rating Q is equal to 30 kVA. Okay. And what are the data they have given? Q is equal to 30 kVA, and other than that, they have given you number of turns in primary and secondary. Number of turns in primary is mentioned as N1, which is 500. Number of turns in the secondary is N2, which is 30. Okay. Other than that, they have given the supply voltage, which is V1 is equal to 3300, and the frequency of the supply is 50 Hz. Okay, so these are the data given in the problem. What we need to find out is to find what are the data to be found? V2, the voltage at the secondary side, V2, and first one is V2, second one is, we need to find out the current magnitudes at primary as well as secondary, I1, I2. Third, we have to find out flux value. Okay, so these are the three data we have to find out from the transformer. So let us find out the solution. V2. We are finding out the first requirement. So V2 can be found out from transformation ratio equation. What is the transformation ratio of any transformer? K is equal to V2 divided by V1, which is N2 divided by N1. which is equal to I2 divided by I1. Can you see the writings of the board clearly? Can anyone turn on your mic and answer me?
Yes, sir.
So the numbers are visible, isn't it?
Yes, sir.
Okay, thank you. So from this detail, we can find out V2 value easily. Okay, so what are the data given from out of these equations? We know the value of N2. N2 is 30, N1 is 500. Okay, so this value they have given. Okay, so we can easily find out, as well as V1 value is also given. V1 is given. Okay, so from these detail, we can easily find out V2 value, which is V1 into N2 divided by N1. Okay, so what is V1 value, which is 3300 into N2 value is 30 and N1 value is 500. Can anyone solve this and answer me for this? 330 into 3 divided by 5. What is the answer?
$198, sir.
198. Can you? Is it exactly 198?
Yes, sir.
Okay, 198 volts. So the first part is solved. Okay, so we have find out the voltage equation, voltage value at secondary side. Okay, next one, we need to find out the current magnitude at full load rating. The transformer, assume the transformer is operating at full load power. Okay, that is the entire 30 kVA power is transmitted to the load. Okay, at this condition, what will be the current value in primary and secondary? So this detail they have given you. Okay, so when it is called full rating, you need to take Q value as it is 30. So in case if they tell you to find out the current value at half load condition, then you need to put this as Q by 2, which is 30 divided by 2, 15. Okay, please understand that. Read out the question properly. They have clearly mentioned that you need to take transformer operating at full load condition. So full load condition means this entire voltage, entire power is utilized. Okay. So to find out I1, I'll simply put P by V formula, or else P equal to VI formula. Okay. So at full load condition, the primary side current, I'm going to measure the primary current initially. I1 is equal to Q divided by V. Or else we can call this as kVA rating divided by V1. So yeah, what is the kVA rating of the transformer? Which is 30 into 10 power 3, and the voltage at primary side is 3300. So what is the value? Which is the numerator, we have 10 power 3. Put that as well and answer me. What is the value of I1?
9.09, sir.
Yes, very good. The current at primary side is 9.09 amperes. That is the right answer. Next, we have to find out the current at secondary side. So use the same theory for finding out current in secondary side. The only difference you have to make is in denominator you have to put V2. You find out the answer me. I2 is kVA rating divided by V2. What is the answer? What is kVA rating? 30 into 10 power 3 divided by V2 value. That is what we found from the previous case. Okay, 198. What is the answer?
151.5.
161.5 amperes.
51, sir.
Yes, that is right. How much?
151, sir.
51. You can even cross verify this with this equation. Now we know the value of I1. I1 value is known. And using this equation also we can find out I2 value. I'll derive that as well. So I2 from this equation, okay. I2 from this equation is I1 into, sorry, this equation has been different only. It should be inverse, okay. I1 divided by I2. I2 is equal to, so what will be I2 from this equation? I1 into, can anyone answer? So I'll write it here. I1 by I2 equal to N2 divided by N1. Okay. K value we don't know. We didn't calculate K value directly, but we are substituting that. Instead of K, we are substituting 30 by 500. You can even put K value. Initially find out K value separately and use that in every equation. Okay. Simply you can put value K here, I1 into K directly. That is very good. Okay. So if I need I2 here, it should be I1. This will go this side and I2 equal to I1 into N1 by N2. It will become N1 by N2, which is 1 by K. Okay. So if you put, you will get the same answer. Okay. So what is the third part? Third part, we need to find out the maximum value of flux generated from the core of the transformer. Okay, so third one is 5M. Okay, so for this, we have to make an assumption that V1 is equal to E1. Also, V2 is equal to E2. So what is the difference between these values? V1 equal to E1, V2 equal to E2. We are making an assumption. So if you assume this, then the transformer is meant to be a ideal transformer. Okay. So for ideal transformer, V1 value will not be equal to, sorry, for a practical transformer, V1 value will not be equal to E1. Okay, V1 is what you supply from the source, AC source. E1 is the voltage induced at primary winding. The supply voltage and primary winding induced EMF will differ based on their winding resistance and winding impedance. Okay, similarly, this is the voltage received at the load, measured at the load, and this is the EMF induced in the secondary winding. Okay, so we cannot transfer the entire induced EMF to the load. Okay, so always for a practical case, V1 will be greater than E1 and V2 will be lesser than E2. Okay, for in practical case, this will be the equation, but we are assuming V1 equal to E1, V2 equal to E2. Since in the problem they have not mentioned any value of resistance or reactance. Okay, since these values are not given, you should make this assumption. Okay, so from this assumption and the EMF equation of a transformer, we know that E1 is equal to 4.44 F 5M into N. So this is the EMF equation of a transformer. Okay, so this is the EMF equation of transformer. What are the data we know from this equation? We know the value of E1, which is V1. 4.44 is a constant, F is a constant, flux, maximum flux, that is the value we have to find out. N1 value we know. Okay, so from this equation, phi m is equal to E1 divided by 4.44 into 50. Frequency value is given as 50 and N1 value is 5. Okay, what is E1 value? 3300. So 3300 divided by 4.44 cross 50 cross 500. So answer me, find out the answer. Can you find the answer for this?
0.029.
0.
0.9.
3300 divided by 4.44 into 50 into 500. You post the answer in the chat box. Post the answer in the
0.029.
chat box. 0.029 is the correct answer. Otherwise, we can write it as 29 point something milliweber. So unit of flux is Weber. Okay. So do you have any doubt in this problem? So the problem is very simple. The important thing you should know is you have to make an assumption when there is R1, R2 values are not given. Okay. Assumption, the induced EMF values are equal to supply values. One thing. And second thing is we need to know the value of transformation ratio. Okay. So these two values we should be knowing. These two equations we should be knowing, and otherwise the problem is very simple. Okay. So we'll go to the second problem. So I'll write the given data for the second problem. I'll read out and you should make the key points of the second problem. Okay. Yes, 6600 volts, 440 bar 440 volts. 6600 bar 440. What does it mean? The primary side it is having 6600 volts. In secondary side it is having 440 volts. Okay, if you just go through the slide, I'll share it again. So look at the screen. So this is the problem. Yeah, 6600 volts bar 440 volts, single phase 600 kVA transformer has 1200 turns in the primary. Okay, they didn't mention the secondary voltage or secondary number of turns. Okay, so they have told you to find out 4 different factors, which are transformation ratio, number of turns in the secondary, voltage per each turn, and secondary current when it is supplying a load of 400 kilowatt at 0.8 power factor lagging. Okay, so that is what we have to derive now. I'll write the given data. Look at the board now. So what are the data given? They have given the voltage ratios, okay, so which is 6600 volts bar 440 volts. Okay, so let us take it as V1 as 6600 and V2 as 440. Okay, next the power value has been given, P or Q, let us use the same notation. Q is 600 kV. And they have given you the primary number of turns, N1 is equal to 1200. Okay. So other than that, no data has been given, and in the fourth part they have mentioned at a load of 400 kilowatt, find out the secondary current. Okay. So that we can easily find out. So these are the data given in the problem. Okay. Then we have to find out, first one, transformation ratio. That is very simple to find transformation ratio, K value. Second one is to find out voltage number of turns in the primary, in the secondary side. Yes, very good. The number of turns in the secondary side, N2. Okay. Third one, we have to find out voltage per turn. So they have simply given find out voltage per turn. What you need to find is, you have to find out voltage per turn from primary side as well as secondary side. You need to find out the voltage turns ratio, primary as well as secondary side. Sorry, voltage ratio. Fourth one is finding out current at secondary at a power of 400 kilowatt with 0.8 lagging power factor. Okay, so these are the details we need to find out. Okay, so let us go one by one. This is also a simple problem, and this question may be coming in 6 marks. Okay, transformation ratio, very simple. Transformation ratio K is given as V2 by V1. Okay. In this problem, they have directly given V2 value and V1 value. Okay. So what is V2? Which is 440 and V1 is 6600. So what is the answer for this?
0.066.
0.066 is the turns ratio of the transformer. K value is 0.066. Yes, very good. Second one, we need to find out number of turns. Number of turns in secondary winding. Same, you can use the same theory, K equal to N2 by N1. And we know the value of N1, which is 1200. So N2 must be K into N1. Okay, so what is that? 0.066 into 1200. What is the value?
79.2, sir.
79.2. You cannot write the number of turns in terms of decimal. So better 79.2.
Yes, sir.
You make a round of it.
80, sir.
Make it a round of figure 80. And 2 is
80, sir.
okay. Since it is a number of turns, you cannot make it a decimal number, isn't it? Okay. So it is either 79 or 80. You make a round figure 80. Okay. Third one, we need to find out the turns ratio. Sorry, voltage per turn ratio. So it is otherwise given as EMF per turn or voltage per turn. Okay. So let us calculate the EMF per turn in primary side as well as secondary side. Okay. So it doesn't have any notation for that. Okay. EMF per turn is given as V1 divided by N1 as well as V2 divided by N2. So directly you can substitute the answer. Okay, V1 divided by N1. What is V1 value? 6600 divided by 1200. Here, V2 value is 440 divided by N2 is 80. So what is the answer?
5.5, sir.
So for both the cases, you will get 5.5 volts per turn. Both of them are getting the same answer, isn't it? So from this, we can identify the EMF per turn in primary side and secondary side should be equal in all the cases, even if the voltage is stepped down or stepped up. It is not a matter of how much voltage is in the primary side and how much voltage in the secondary side. So it is very evident that when number of turns increases, the voltage also will be increasing. Okay. So what are we calling a step-down transformer? Step-down transformer is called as the one which is having reduced number of turns compared to primary in the secondary side. Okay. So compared to primary side, secondary side number of turns will be lesser. That indicates when number of turns increases, voltage will be increased, and number of turns decreases, voltage value will be decreased. Okay. But what we will keep balanced is the power value. The primary side and secondary side power will be maintained equal. Okay. So then only it will be called as a better transformer, isn't it? So when losses are less, you just imagine we are having a lossless transformer. So lossless transformer means the entire power which we are giving as an input will be transferred to the output side. Okay. So that means the voltage and current, the product of voltage and current in primary and the product of voltage and current in the secondary should be equal. So that is made equal by means of this voltage per turn. Okay. So third case we have found out in primary as well as secondary, This is equal. EMF per turn is equal. Okay. So what is the fourth one? Current in secondary at delivering a load of 400 kilowatt with a power factor of 0.8 lag. LPF means lagging power factor. Even leading power factor is also denoted as LPF. And lagging, LAG, lagging power factor. Okay. So P is equal to, this equation may be familiar to you. P equal to V2 I2 cos phi 2. For any AC system, we are always considering the power factor as well while calculating the power. Okay. Voltage, current, and power factor in the secondary side. That is very important. The reason for including power factor is the load may be of resistive or inductive. Okay. So since they have given that as 0.8 lagging power factor, the load must be, what type of load must be used? They have given it is 0.8 lagging. Okay. So what type of load must be connected in the transformer? Can anyone answer? The load must be of inductive nature. Okay. So inductive loads only offer lagging power factor. That is, current will be lagging the voltage by some angle, particular angle. Okay. There will be a delay between voltage and current. Okay. So from this equation, the unknown value is I2. We know the power value, which is 400, is directly given. I2 is equal to P divided by V2 into cos phi 2. Okay. So I2 is 400 kilowatt. Okay. So you should write that as 400 into 10 to the power 3 divided by, what is V2 value? 440. And power factor value is given as 0.8. What is the current magnitude?
.17 ampere.
909. But I get a different answer. Do anybody having a calculator? Wait. 400 into 10 to the power 3. I'm getting 1136. 1136.36, isn't it? Okay, that is the answer. So that is the answer. Very good. So now we have included the power factor as well. The current at the secondary will be 1136.36 ampere. Okay. So with this, the second problem is over. We will do one more problem, and I'll ask you some questions in the previous class. The next question is very simple. You can find out easily yourself. I'll assist you. look at this problem. It's very simple. Only one question is tricky here. We need to find out the maximum flux density. That term we did derive, but you know what is flux density? The relationship between flux, a cross-sectional area, and flux density. Okay. So here they've asked you to find out the maximum flux density value and the aim of inducing the secondary side. Okay. So read out this problem. I'll just read out and you just write down the given data. Okay. First one is they have given the primary and secondary turns. Okay. A single phase transformer has 500 turns in the primary and 1200 turns in the secondary. Okay. Let's write them. Here, what are the data given? A single phase transformer has 500 turns in primary and 1200 turns in the secondary. N1 value is 500, N2 value is 1002. Okay, and the cross-sectional area of the core is 80 centimeters square. Okay, cross-sectional area A is given, which is 80 centimeters square. So we have to calculate everything in terms of SI units, convert that into SI unit, which is 80 into 10 to the power 4 meter square. Centimeter, the value has been given in centimeter. While converting that into meter, I have to multiply that with 10 to the power 2, minus 2. Okay, here it is centimeter square. So 10 to the power minus 2 whole square will be 10 to the power minus 4. So that is what has been written here. So cross-sectional area is 80 into 10 to the power minus 4 meters square. Okay. Then, if the primary winding is connected to 50 Hz supply at 500 volts, calculate the flux density. Okay. So they have given frequency value F equal to 50 Hz. And supply voltage V1 is equal to 500 volts. Isn't it? Just 500, isn't it? Yes, 500 volts. So what they have told you to find is maximum flux density. Second one is they have told you to find out the EMF inducing secondary side, E2 value. So what I told you in the first problem, if resistance values R1, R2, X1, X2 values are not given in problem, if they are not mentioned, then you need to consider V1 is equal to E1 and V2 is equal to E2. Okay, so please keep that in mind. After solving 10, 15 problems, you will get a confusion whether to take V1 or E1. Okay, because in some problems they would have mentioned V1 value as well as E1 value. Okay, or in some problems they would have given you V1 value and R values, R1 and X1 value. So from this, how to find out E values. So those will be explained. Those problems will be derived in the next class. So I request you to bring calculator, keep calculator with you tomorrow for the first session. Okay, tomorrow first session is transformers and induction machine. So these are details we have to calculate. Okay, solution. Supply voltage is given. V1 is 500 volts. Okay, so what is the formula for induced EMF transformer, E1 is equal to 4.44 F phi m into N1. Okay. So we know the value of E1, which is equal to V1. Put that here. 500 is equal to 4.44. Frequency value has been given, which is 50. And phi m value we don't know. This is not given here. N1 value is given, which is 500. Okay. So what is phi m? 500 divided by 4.44 into 50 into 500. What is the answer? Maximum flux value is phi m is equal to can anyone answer?
$4.5 milliweber.
Yes, very good. 4.5 milliweber. That is the answer. Very good. So flux value we have find out, and flux density, the equation for flux density is Bm equal to phi by A. Flux per unit area is called as flux density. In a particular area, so for example, in 1 cross 1 meter surface, how much flux is generated? That is called as flux density. Okay, so it is taken for a unit area. Unit area means 1 meter square area. In 1 meter square area, how much flux is generated is called as flux density. So phi m value we have measured, which is 4.5 milliweber, and the cross sectional area A is 80 into 10 to the power minus 4. So substituting that, we will get 4.5 into 10 to the power minus 3 divided by 80 cross 10 to the power minus 4. The answer would be Bm is equal to yes.
0.56.
Yes, very good. 0.56 Weber per meter square. So it is not milliweber, it is 0.56 Weber per meter square. Don't forget to put the unit, you will lose 0.5 marks for that. You forget to put the unit. While evaluating, will be clear, you should be mentioning all the units properly. Okay, next one, what we have to find out is the EMF induced in the secondary. I want you to do it yourself, which is very simple, derived in the last two problems. Find out induced EMF in the secondary side. So they have given N1 value, N2 value, and V1 value. All these values has been given. So find it yourself and answer me. Use the transformation ratio equation. You can find the E2 value in two ways. Either you can put EMF equation, either you can use this equation, EMF equation, for the secondary side. In case of secondary side, it should be written as E2, and here it should be N2. Either you can use this equation or go for transformation ratio on that one, K equal to V2 divided by V1, which is equal to N2 divided by N1. Use that formula. You can use those two formulas. Any answers?
.1198 volts. So
1198.8 volts, which is almost 1200 volts. Yes, very good. 1198 is right. So for those who don't know that, please look at the board. V2 is equal to N2 divided by N1 into V1. Okay, it says 500. What is N2 value? N2 is 1200. V1 is 500, which is 1200. Or we can use this method, 4.44 F into 5M N2, which is 4.44 F. Sorry, F is 50. 5M value is 4.5 into 10 to the power minus 3 into 1200, which will give you 1198.8 volts. These two are more or less equal. The reason for the 2 voltage reduction is here. Okay, so we have taken only one decimal after the point, only one part after the decimal point. So if you take fully, it will be 1200 volts. Okay, so in both the cases, we are getting the same answer. Okay. So today we have derived 3 problems, and I request you to keep calculator with you for tomorrow's class. Tomorrow also we will be deriving some problems, and still vector group is pending in the first module, and I will complete that in the next class. We will derive some problems and do the vector grouping. And one more topic we have is tap changing transformers. Okay, so only 2 topics we have pending in first part of second module. Okay. So I'll ask you some questions. I'll read out some names. Please answer the questions. Bharat, MG Bharat, please turn on your mic.
Yes, sir.
Yes. What is called transformation ratio? Bharat, answer me.
The
What is
secondary
called a
voltage,
transformation ratio?
secondary voltage by primary voltage, sir.
Ratio between secondary voltage to primary voltage is called as transformation ratio. Okay, very good. Darshan, turn on your mic. 205.
Yes. Yes, sir.
Some are
Sir.
Darshan. Yes. If K value, if the transformation value is more than 1, greater than 1, the transformer is called as what?
So once again, sir. Hello.
If K value, K, transformation ratio, V2 by V1 ratio is greater than 1, the transformer is called what transformer? V2 by V1 is greater.
Step-up transformer, sir.
Then you'll be having question next. Voice is breaking. Is it so?
Yes, sir. சரியா புரியல sir.
Huh? Okay. Okay, Darshan, that is the answer. Step-up transformer is the right answer.
Thank you, sir.
Okay, and Sanjeev Kumar.
Sir. Sir.
What are the types of three-phase transformer connections? What are the types of three-phase transformer connections?
Star star.
Yes.
Star delta. Delta star. Delta delta.
Okay. What is open delta connection? If you don't know, just tell, sir, I don't know, sir. I'll not go to beat you. Okay. We'll call the next one. And now, Suganand, now it's your turn. Turn on your mic. Suganand.
Sir. Sir, கேக்குதா?
What is the purpose of? Yes, audible. What is the purpose of Buchholz relay?
Sir?
What is the purpose of Buchholz relay in a three-phase transformer? While teaching about construction of auto transformer, I told you Buchholz relay, a protective device. What is the function of it?
So it's a security device for alarm.
Okay, it indicates that there is a fault is occurring inside the machine. Okay, very good. Just mute yourself. Next one, I would like to call out a lateral entry student. Nishant, turn on your mic. Nishant?
Sir?
Yes. The question for you is, can you tell the two differences between core type transformer and shell type transformer? The next session is also mine, so we will be continuing this session. Nishant, are you online?
Yes, sir.
Comparison between core type transformer and shell type transformer.
Sir, motor.
Motor. I'm asking about transformers. Okay, if you don't know, just leave it. Mute yourself. So with this, today's class is over for transformers and induction machines. And fourth session is all about, we are going to see a virtual lab. I'll request you, I'll share a link to you. Just go through the link and keep the mic turned on. Sorry, keep the mic turned off and keep the speakers turned on.